Hey, welcome back. Let's have another look at another piece of the IBM server puzzle. This little module, well, it's not little, it's quite long. It's 19 inches long, 4 inches wide, inch and a half tall. This is actually a power supply unit for one of the processors. Now each processor has two of these power supplies for redundancy, and these are fully hot swappable. If one gives out, they can pull it out and replace it while the computer's still running. This power supply is all self-contained. It takes in the 350 volts and converts it down to the voltages that the processor, the CPU, will use. Like I said, it fits in a slot in the processor housing. It just slides right in all the way, all 19 inches of it, and then this connector has to engage. This connector will drop down, and they use kind of a unique mechanism, this locking thing here, and when you spin it down, the connectors drop into place and make contact with the other connector inside the CPU unit, and you got contact, and it's locked in. Ventilation's from end to end. This side is perforated for ventilation. This side is perforated for ventilation, and that's all the airflow it gets. There's a couple of lights on the end here too, LEDs. Sorry, 3 LEDs. One is a fault LED, and then there's 2 LEDs, one for power in, one for power out. So, and it's quite heavy, it's very heavy. Probably weighs maybe 10 pounds. So let's open this up and see inside. But first, let's read the nameplate and see what kind of specs it has. And as you can see, it's got water damage. Alright, so this module is a DCA EPS. It's made in Taiwan. It takes an input of 350 volts at 8 amps and has multiple outputs. We got 4 outputs of 1.2 volts, 105 amps, 18 amps, 6 amps, and 210 amps. Actually, these multiple outputs, 1.2 volts, is 105 amps, and there's 4 supplies. So that's a total of 420 amps total. And same with these other ones. This 18 amp, there's 4 of these, and these are single 6 amps and 210 amps. And then there's a 1.8 supply for the CPU, 8 volt, and that's at 150 amps. And 3.3 volt supplies, 6 amps, 20 amps, and a 10.9 volt. I don't know what they would use that for at 6 amps. But all of these supplies are for this the CPU and the memory. Again, it has on the end it's fully gasketed for RFI suppression. This is metal fabric gaskets, and it's all the way around, just to keep the RFI suppression down. So let's open this up and have a look. Okay, screws are out. Let's lift the lid. We've got an insulating sheet. It's a full steel case, and inside we have multiple buck converters all wired in here. So let's have a look at this. Let's pull the board right out if we can, and take a good look at this, if I can figure out how to get it out. So inside we have the loading mechanism that loads the power supply into the CPU or processor housing, and it works on a principle of inclined plane, and it slides. So it's all metal pieces. And you know, everything's custom machined to a tight tolerance. Looks like everything's been CNC'd. Even this part where the screw, looks like that's all been CNC'd over top of that screw. And this is the module, or the power supply itself. So we have a 350 volt input, and I'm assuming that is going to be these pins here. And it looks like we have a little bit of power conditioning here. There's a choke and a double back-to-back diode. And then there's 4 modules here. It's called parallel bus converter. There's a module here. Pull it out. And this is an MDC-E card for Easy Clip, E-Clip Z. And it's got an Altera Max processor on it. And this is probably the brains of the operation here. This will control the power supply and monitor the, its state and condition. And then we have a load of buck converters. We got 11 total. Everything's soldered to a backboard, and there's not much for components on this. This is all pretty much just interconnection. A couple of surface mount diodes. There's a few little tiny caps here. Some resistors. Not much to speak of. All the action's happening on top here with these buck converters. And these are, let's see, 1.8 volts at 125 amps, 1.2 volts at 175 amps, 1.2 volts at 175, and so on and so on. This one here is 1.2 volt at 16 amps, 3.3 volts at 16 amps, 3.3 volts at 45 amps, 12 volts at 16 amps. So this one's probably doing all of the miscellaneous voltages, and then we have banks of buck converters for the 1.2 volts. Here's a 30 amp, 30 amp, 30 amp, 30 amp, 195 amp, 195 amp, 195, 195 amp. This is a 1.8 volt at 125 amps, and that appears to be it. So what are these little buck converters? Let's have a look at those. I'll take some out and we'll have a look at them. So here's one of the buck converters. This is a 1.2 volt 175 amp. It's got a date code of 09 of 10 of 09. I think this one is a later unit from the other ones, but let's look at the construction of this. It's got full copper heatsink. If you can see that. It's got a copper plate, and then the fins are attached, and they're soldered in place. Because when I removed one of these, I got it too hot, and the solder and the fins fell off. So they're soldered on. But let's have a look inside here. Separate the heatsink from the rest of the board. So if you do the math, 1.2 volts at a 175 amps. That's something like 200 watts for this little converter. And let's pull this off. Did I get them all? Yes. Okay. So we have the heat conducting paste. It's almost like a putty. It's not like your regular sill pad. It is actually a paste, and that provides thermal conductivity between the semiconductors and the heatsink. Now these are all MOSFETs here. Scrape this off so you can see it better. Let me clean this off, I'll be right back. Alright, so each buck converter has its own controller, and it's got 6 channels. There's 6 buck converters ganged up together to produce the 175 amps. And each one has its own controller, and then it has a, it's a controller that oversees everything, makes sure it's all working. On the back, each buck converter has its own set of MOSFETs, and then there's one MOSFET here. I believe this is the power input, the 350 volts input, and this might be a fuse. Can't really see very good. So we got power in, MOSFET, probably to turn the device on and off. I think that's our fuse. Control, all on this end and this end, and they have control lines here. Power input on these 3, I'm guessing, or maybe 2. Maybe the third one is a ground. I think that's a ground. But anyways, got 6 buck converters, all tied in with parallel, and these pins on the bottom, they alternate between your output power and ground, output power ground, because every second one is insulated from the ground plane here. Looks like this is made by International Rectifier. They got their branding on it. Some of these MOSFETs are, I should have a look at some of these MOSFETs. Each buck converter has its own inductor and bank of capacitors. There's 4 capacitors for each one. And let's take one of these inductors off, have a look. There we go. As you can see, it's a flat. It's not a wire. It's a flat conductor. So 2 millimeters wide, maybe 0.5 millimeter thick, and it's wound on these. It's just, well, they're air wound, and then it's encapsulated with this ferrite material to give it a really high quality inductor. So it looks like we got 3 turns, or 2 turns on the inductor, the caps. It's pretty basic for a buck inductor, buck converter. So if you are aware of how a buck converter works, is you have your MOSFETs switching on your input voltage. They switch at a high frequency on and off, and what they do is they create a current that is fed to the conductor or the inductor, and then the inductor, depending on its value, will either boost it or buck it, the voltage, now up or down. And then the capacitors on the output will smooth out the impulses or pulses and provide a steady DC voltage. Let's see what value these capacitors. I think they're probably around 10 microfarad. Let's try one of these out on my tester. If I can get it in. Oh yeah. Where'd it go? Take out another one. Let's see if we can read this. And I got 10.5 microfarads, so that's probably, and then we got 4 of them, so it's 42 microfarads. So they configure these in many different ways. This one's configured differently. It's got 4 buck converters, and you can tell by the 4 inductors and the 4 sets of capacitors. There's 4 controllers, and what does this one say? This is a 1.2 volts at 16 amp, 3.3 at 16 amp, 3.3 at 45, and 12 volt at 16 amp. So yes, 4 different voltages, and you know, they're flexible. Here's another one that's got 4. These are 1.2 at 30 amps. So we got each buck converter is providing 15 amps at 1.2 volts. A little different configuration. And this one here is 1.2. Another one. So you can see they can, from all the different configurations, they can pretty much build any module they want. Now this is a little different. This is a heat sink. This isn't copper. This is some kind of pot metal. And let's have a look at this. What is this? This is a parallel bus converter. This is produced by Vicor, and I think they made this module. So we've got out positive, out negative, out positive, out negative, out positive, out negative, out positive, negative. I don't know what voltage they're going for here. And then they've got control and positive and negative in voltage. So it's very basic. It's got 1 voltage in, a control pin, and then all these outputs. Let's see if we can open this up. Alright, so I got a little angry at it and I took it apart. So it comes apart, it's got a board. On the input side of the board we have a fuse, and then we have 2 inductors, probably just power conditioning inductors. There's a small coil there, you can see it. You can see copper in there. Everything's potted in a heat conductive, it's not an epoxy, because it's very soft, but it's a heat conductive filler. Let's call it a filler. And inside the lid, or the heat sink we'll call it, there's two of these modules. One was positioned here and one was positioned here. These modules are called bus converter module, BCM, and this is made by VI chip, and these are self-contained modules that gotta pull up a data sheet here, I'll show you. So these are isolated fixed ratio DC to DC converter modules, and these feature ultra high input voltage from 400 to 800 volts, or high voltage 200 to 410, which is where we are right now, and they have very high efficiency up to 97%, and probably closer to 98%. And they have very high power densities of 2800 watts per square or cubic inch. You can parallel the inputs and outputs for high power arrays, and you can connect inputs in series for higher higher output voltages. And the ones I got here are the full VI chip. And for, let's see here, let's take a look at this. The full VI chip ones are analog devices, and they run around 200-300 watts per device. If you go look at the data sheets, this is not the correct data sheet for this item because this is 10 years old now, 12 years old. These are probably the most current devices they have on offer, and then it shows the typical applications of you got your 380 volts input, and you got your high voltage bus converter module, and it knocks it down to 12, 24, or 48 volts, and from there you can do your buck converting. But these are isolated. That's what I was wondering about all these power supplies and whatnot. Nowhere did I see isolation, but here it is. This is the isolation right here on this device, and I don't know what output voltage these are. If I looked up the data sheet for this one, it'd probably tell me. But now it's all starting to make sense. 350 volts input, bus converters. We got 8 of them. There's 2 in each package, and they're capable of about 300 watts each. And then that's isolation as well. There's our isolation from the mains because there was no isolation previous. And then we got our buck converters. These are running on the lower voltage. I think these run on 48 volts or something like that. These don't run on 350 like I first thought. And yeah, that's how they do it. And everything's monitored and controlled with these little processors. And it goes back to the host controller, the flexible, what is it called? Flexible service processor. And that is the watchdog computer that watches the main system. So that's all there is to pretty much a processor power supply. And like I said, there's 2 of these for each processor, and they're fully redundant, hot swappable. If one dies, they can pull it out and replace it with another one with the computer running. And yeah, quite a setup. So I think next we have more to do here. We got more components to look through, and I think it's going to get interesting. All right, thanks for watching.